Good morning. I hear myself at least. Yes, I'm René Laureijs from the European Space Agency. I studied, in fact, here in Groningen at the Kaptein Institute, and I'm an astronomer. And I've worked on several missions, and my last mission is now Euclid. And indeed, it's an extremely exciting mission. Although we still have to launch this satellite and get it in place. We are at the moment close to the milestone where we have all the components, and after these milestones we put all the components together in order to get a real flyable spacecraft. Now what do we want to do? Do cosmology with Euclid. And what I'm going to explain today is that we have a number of requirements given by the cosmologists to do cosmology with Euclid. And I'll show you what type of hardware comes out of this and what type of mission you would design from this. We only have to measure a few parameters. So this is the dark energy equation of state, WA, the modified gravity constant, the growth rate, dark matter. We can also translate this in the neutrino mass, and the initial conditions parameter, the non-linearities part. Now, what we want to do with Euclid is to make a decisive measurement of the accelerated expansion of the universe. Decisive, Henk already mentioned it. We have a measure called figure of merit, and we want to have this figure of merit as big as possible, and it gives us an idea how accurate we can measure these parameters. Now, we have two. The satellite is designed, the mission is designed towards cosmology, and especially cosmology on two probes. One of these have been explained by Henk in rather detail. One of the probes is weak lensing. So what you want to measure from a measurement point of view is basically small distortions in the shapes of galaxies. And these galaxies are small by themselves, and you want to measure the ellipticities and the variation in ellipticities over the surface of the sky. Now, the galaxies themselves, in order to get enough statistics, are of the order of a fraction of an arc second. And measuring the ellipticity is not that difficult, but measuring to know how accurate you measure this ellipticity, that's the problematic part in this mission. We also measure galaxy clustering, and we do this by accurately determine the redshifts of galaxies themselves, and knowing their redshift and their positions on the sky, we can determine the change in the structure on the sky as a function of redshift. Now I've given here this plot saying that you have a typical scale length in these structures, and this scale length will expand with the expansion of the universe. And there is a typical scale length here called the first acoustic mode here that grows with the age of the universe, and with that we can determine the exponential acceleration of the universe. Why do we have two probes, galaxy clustering and weak lensing? Why they are helping us in understanding the cosmological systematics. Good example is this one here. We have here two parameters. This is the growth parameter, and this is the parameter in the densities. If we do galaxy clustering, we constrain in this plane the uncertainties in this way, in this direction. If we do weak lensing, we constrain it in the other direction. So both of them give a much better determination of the parameters. While in terms of systematics, the whole ellipse here from galaxy clustering could be moving in this direction, And if we make an error in reclancing, this ellipse could also move in a certain direction. So what we want to do is, by having the two probes, determine the best position in this plane. Now we can have other priors as well, and Henk also mentioned this, is for instance coming from Planck, although Planck doesn't constrain too much in terms of dark energy. It can help us as a prior, and it will help us also in pinpointing the precision of this of the numbers. Okay. Well, what do we measure? We would like to have a three-dimensional uh, picture of the galaxies on the sky, and we want to have well, it's the position on the sky as well as the redshift, which gives us a three-dimensional picture. And for that, we need a lot of statistics to do that. So we have of the order of a few billion galaxies. Where am I? Yeah. Of the order of a billion galaxies, 1 to 2 billion galaxies for weak lensing, which we want to measure ellipticity. Since the sizes are of order of a fraction of an arc second, and I give here what an arc second means, because it's not well appreciated as astronomers to understand exactly what an arc second is. It's about half a millimeter at the distance of 100 meters, so this is the angular distance of half a millimeter at 100 meters. And we need to measure more than 25 million galaxies for the galaxy clustering experiment. So we do these two dark energy experiments with a high precision and a minimum systematics. So we need information on the scales of the point spread function of the telescope, and that is of order of 0.1 arc second. We want to detect 30 galaxies per square arc minute, so this is about 110,000 galaxies per square degrees. And weak lensing demands a minimum of systematics, so we need extremely high stability for our telescopes and a detailed system knowledge. So we want to have a high stability to understand the variations in terms of system knowledge. If something happens, if we do a slew, if we point from one position to the other, we know what happens to the telescope and how our measurements are affected by it. And that can only be done by understanding the system as good as possible. Once we understand all these issues, we can model it, at least Henk can model it, and get the best cosmological parameters out of this. We also want to do spectroscopy in the infrared, and that is from 1 to 2 microns, which cannot be done from ground and has to be done in space. So what is our first design solution for getting these requirements done? We go to space, and we go to the second Lagrange point, which is basically the point where if you rotate around the sun, pulled by the Earth and the sun, you co-rotate with the Earth and the sun, and the fact that that at a certain distance from the Earth you are basically at this co-rotation, and you have a minimum in the gravitational field. It's very stable there, also from a radiation point of view, and for a weak lensing experiment, it's an ideal place to be. Another advantage of being in space is that you can see the whole sky. I mean, if you have a telescope on ground, you see only half a hemisphere at best, or you have to go to the south to see the other half. But in any case, if you have one telescope, go to space and you can see the whole sky. We have no atmosphere in space, so we can, in this wavelength region, we can observe much better than from ground. In fact, it's the best place to observe it. Since we have no atmosphere, the telescope can achieve the diffraction limit. So we can afford a 1 meter class, a small class telescope, since the point spread function of this telescope can be built diffraction limited to about 0.49 second. Since we have some blurring from ground, if we make this if we make this comparison, so 1.2 meter is almost equivalent to a 4.5 meter aperture from ground. So a 1 meter class telescope is a several meter class telescope from ground. We have a problem in space that we are mass limited. We cannot just build our experiment without consideration of how heavy this experiment will be. So a small telescope is good. The other advantage of a small telescope is that it can have a very large field of view. Nevertheless, the design is very difficult for this telescope. In order to get a good stable experiment, our whole telescope, including the truss and all the mirrors, is built of silicon carbide. So if changes occur in terms of temperature, the silicon carbide, since it's all made of the same material, the silicon carbide, all components will expand in the same way, or shrink in the same way. And this way the image quality will be very stable. Now the curvature, for instance, of the main mirror is very well determined. However, for the accuracies we want, so measuring the shapes of galaxies to get the ellipticity, we have to get the ellipticity of the point spread function as small as possible. For that we need a very accurate polishing of the telescope. And we are at the moment at the point where the measuring device of the polishing is also difficult to quantify. So we have really to measure deviations of the order of nanometers, and for the at the moment we find a small astigmatism, and spent several weeks discussing whether this astigmatism is due to the measuring device or really due to the fact that we have wrongly polished the mirror. Now this is what it will be. This is a computer-aided design model of the telescope. So it looks smallish, but still the main mirror is about 1 meter here. So this is the other side. If you rotate the mirror, then the light goes through the base plate, as we call it. This is the base plate. If you rotate the whole structure, then you see the two instruments. One is an imager here, and the other one is the spectrograph. Okay, what do we need? We need a very large field of view in order to measure a very large area on the sky. A large field of view we can achieve about half a square degree per image we can take. Now half a square degree is still small compared to the sky, of course, because we want to survey 15,000 square degrees. If we compare it with James Webb's Space Telescope, its biggest field of view is about 2 by 2 arc-minute. So if we compare Euclid with JWST, it's really amazing how big the field of view is. We have a little undersampling of the PSF. We use for our imaging 0.1 arc-second pixels, and the PSF itself, the full width half maximum, is 0.14 arc-seconds. We overcome this problem by dithering around, so taking several pictures of the same piece of sky at different positions. The mission lifetime is 6 years, so that helps us in having sufficient time to cover the sky area. And another problem is that the measurements, what we want to do, measuring the ellipticities and doing spectroscopy, cannot be processed in orbit. That means that we have to download all the data down to the best resolution, and a way to download so much data is to compress it first. The other thing is to have a fast link to Earth, and with a high bandwidth. So we had to install a new band, the K band, to achieve 850 gigabit per day in data rate from the satellite to Earth. So this is the implementation basically of the satellite. We have a diffraction limited telescope with a visual imager, in the visual, and we have a near infrared prism spectrometer operating in these wavelengths, and also an imaging in the YJ-H bands. From a technical point of view, we have a very complicated attitude and orbit control system, which can give a very stable pointing of a few milliarc seconds. Now, to give you an idea how good, how well Euclid does, this is the famous Eagle Nebula, the Pillars of Creation done by HST sometime. This is the camera HST. So this is a 7 by 7 arc-minute image from ESO, where this HST image is placed. And this is the field of view of Euclid, basically. So this is 42 by 44 arc-minutes. So there are a lot of HST fields in one frame of Euclid, and in fact, in one day, Euclid has done more imaging than HST in its entire lifetime can do. We are collecting information, so we have 36 CCDs, 4 by 4K. We have 16 infrared sensors. The quantum efficiencies of these devices are extremely good. They are of order 90%, so 8 out of 9 photons are registered. On top of it, the noise is extremely low as well, so whatever falls on the telescope will be registered, basically. We can go deep within reasonable integration times. And if we do one exposure, one block observation, because in order to maximize the observing time, the infrared channel and the visual channel are observed in parallel, so we take them simultaneously. So we do of the order of these observations, so block observations, of the order of 20 of them per day. So we can observe of 10 square degrees of sky per day. And even with 10 square degrees of sky per day, we need 6 years to get the survey area. So I hope it doesn't come very well on this here, but this is the area we're going to survey. The different colors gives different seasons of the year, of the 6-year period. So we try to avoid the galactic plane. It's not interesting for cosmologists. And we try to avoid the ecliptic plane here because of the high ecliptic background. It is light which increases the noise in the observations, so that the signal to noise for the targets we want to observe is low. Now, not everything is as fine as you could think of, but because if you look at the raw data, this is a simulation of a Euclid frame. You have a lot of junk inside. And this all has to be cleaned. These are cosmic rays, by the way, and electrons passing by. So these can be easily removed because we dither around on an image. We have also ghosts here because we have a dichroic. These can be removed as well. And there are large groups within the Euclid consortium, so the scientists working on the Euclid data who find algorithms or are developing algorithms now to make these images extremely clean and understandable. Now, this is the type of images you get from the spectrometer. In the infrared detectors are less sensitive to these cosmic rays. To give you an impression of the amount of work to get these images down from the spacecraft and to make science out of it, I show you one plot about the data processing organization we have. So these boxes here are groups of people, groups, developing algorithms. We call them processing functions. And this is the data to be shuffled between them. Mind you that Euclid will do what can be done in space, but what can be done from ground will be done from ground. So ground-based data is an important aspect of the Euclid mission, so it's here. It also enters the pipeline. We call them OUX. This is the external data will be processed together with the imaging of Euclid in order to get an accurate photometric redshift. Now, in the end, we will have our 5 numbers or so to get the cosmology right, and that will be done basically by this group of people. It's a very large group called Level 3 group. Now, what is the development timeline? At the moment, we are, as I mentioned, somewhere here. All the components have been built, tested, and can now be integrated into one spacecraft, and that will be tested again at system level. And we will have a launch by the end of 2021. Could be also in 2022. It's still not sure when this launch date exactly will be. And then we will have a mission of 6 years. So the data, the final data, will be sometime around 2028, 2029. Now, we expect to launch it in 2022. We get all this imaging, so not only cosmology is inside the data, but a lot of other information. So we get imaging down to 25 magnitude, and in the visual, and in the infrared down to 24 magnitude and more. We have spectroscopy, and we can extract lots of catalogs of all the sources inside. So besides the cosmology you can do, there is a lot of other data, not only of galaxies, but also from of stars and galactic sources. For the astronomers, 14 months after the start of the nominal survey, there will be a first release. We will release 50 square degrees to show what Euclid can do for you. And I think this data set is already enormous in terms of what has been done from space and for surveying. But then 1 year later we have a data release 1, which is about 2500 square degrees. So that will be released to the public. We are busy trying to get the archive and the data centers in place to let the astronomer in the world look at the data and work with it. Now the final data release, we called it DR6, is 6 years after Q1. So it's about 2028. And there we will release all data, the 15,000 square degrees, so the entire survey, plus possibly other parts of the project, which is called deep fields, where we look at specific areas on the sky and go a few magnitudes deeper in surveying. The legacy value of these data is enormous, as you know, and the amount of information that can be extracted is also enormous. So that is a challenge for the community to work on this. And I stop with this.
Thank you. Thank you, René. We're a little bit behind time, so let's not eat too much into the coffee break. But if there are any questions, we can take a couple. So I have one. It's for someone from the European Space Agency. You were remarkably vague about the launch date. 21, 22. Can you say a little bit more?
Yeah, it's a big project. It is one of the bigger projects in the European Space Agency, and these projects have a lot of steps to go through, especially in putting it together and synchronizing the deliveries. And because of that, during the integration, all things can happen. Especially when you're testing the things at the system level, there could be elements which might be improvement or further adjustment, and that can take extra time. It's as simple as that. And we aim, of course, from a project point of view, to launch at a certain date, because if you wait longer, it becomes more expensive. But we also want to have a good mission, and we want to have a good balance in the risks you take and the quality you can get in the end. And there are certain points where you have to wait in order to minimize the risks. Otherwise, you can.
Any other questions? Everyone wants coffee. Okay, then let's break for coffee. The speakers between now and lunch, can they go and see Margot with our presentation so we have everything set up? And let's meet again here.